In this part of our discussion today, we'll take a look at mediation. What is mediation and how can we test for it? Basically, it's a hypothesis that there is a causal chain of effects. For example, self-esteem leads to higher optimism, which in turn leads to better grades. And this is just a simple classical mediation model. But sometimes you want to combine mediation and moderation. So it's essentially the same model, but into this model we add an interaction term between a predictor and a mediator. And then this would be called, in a more complex way, conditional indirect effect model. But let's take it slowly. Mediation was proposed in the early 1980s by two guys, Baron and Kenny. Kenny is still alive and he has a nice website. You can find the link here where he explains everything about mediation. But the logic is very simple. You have two variables, x and y. The regression coefficient of y on x, if you use x as a predictor, will be c. If you have a causal chain x, m, and y, if you include into regression both x and m, the regression coefficient will be c with this mark. And if c with this mark is non-significant, it suggests that the association between x and y is fully accounted for or fully explained by m. And then the product of these regression coefficients of m on x and y on m, the product of these regression coefficients a and b, will be called indirect effect, because it's the proportion of variance of x that is shared with y through m. So essentially we are interested in estimating those indirect effects. And when Kenny proposed this approach early on, with Baron they proposed these three easy steps. That first you calculate correlations between x, m, and y, and then you check in regression if m remains a significant predictor when you include x and m as predictors of y. And if x stops being a significant predictor, then you have mediation. And you can say, tada, the association between x and y is explained by m. However, these criteria are now obsolete. Preacher and colleagues have explained that correlation is not always necessary, as Kenny had argued early on. And also the approach that Kenny proposed, which was called Sobel test, it's also obsolete. So do not do this the way Kenny proposed, because nowadays there are much better ways to test for mediation. The Sobel test basically calls you to conduct those regression analysis, take coefficients, multiply them, and use t-test to test for significance. Unfortunately, the distribution of this indirect effect of this product is not quite the same as the t-student distribution. That's why in order to estimate it, we need to use this approach which is called bootstrapping. When we simulate different data sets based on our sample and we average the results across those data sets, and also we based on the results from each data set, we get a distribution of all possible values of this effect. And based on this distribution, we can estimate our standard errors. This approach is available using different tools. Unfortunately, the standard version of SPSS is not able to deal with mediation hypothesis. You need a path analysis package, AMAS, which goes together with SPSS or any other like M+ or R. But in SPSS, you can test this type of models using a special add-on, which is called Process Macro, which is available to download free of charge from the website of its author, Andrew Hayes. Or more easily, you can use Jamovi. Jamovi is a nice piece of software which I have already advertised to you, and it includes two modules which you can use to test for mediation, MedMod and Jam. So I will just show a quick example of how we can test for mediation using this Jam package. So the substantial question that we can ask is the association between gender and year of thesis is fully of gender and year of thesis with somatic symptoms. Is this association fully counted by perceived stress? So theoretically, if perceived stress is a full mediator of the association between year of study and somatic symptoms, we would say that doctoral students who fall sick during their graduate school, they do so also when they experience perceived stress. So probably it's because of perceived stress, but we are not sure because we don't have any longitudinal data. We cannot claim a causal association. So technically, it's very simple. In Jamovi, you install a module which is called Jam, and you enter your dependent variable, your mediators, you can have several ones, and predictors. Here they are called covariates. So your predictors can be either nominal or ordinal, then they will be called factors and they will be dummy coded, or they are called covariates, and then these are just interval variables or dummies like gender here. So what happens when I just run this model? Jamovi gives me a nice graph which reminds me of what my model looks like. Unfortunately, it does not plot coefficients, but it's not too bad. And it gives a nice table here, which is called indirect and total effects. So indirect effect is basically the proportion of variance of gender that is shared with symptoms and also shared with perceived stress. So we say that it's the proportion of variance that is mediated by perceived stress. And we see that here the B coefficient is 0.76, the beta coefficient standardized is 0.06, so it's fairly weak, but still it's statistically significant, it's non-zero. And the same for the year of thesis. The year of thesis, its mediated portion is 0.08 beta coefficient, and it's 0.001 statistically significant. Here you can see estimates for these individual regression paths, for example, from gender to perceived stress, from year of thesis to perceived stress, and so on. B and beta coefficients. So essentially, it's a bunch of regression models. And direct effects, the direct effect of gender on symptom checklist, and the direct effect of year of thesis on symptom checklists. We look at those direct effects to see if the remaining direct effects are statistically significant. So here we see that for the year of thesis, the direct effect, it's not significant. We can say it's zero. So for the year of thesis, we can claim full mediation. We can say that the association between the year in graduate school and somatic symptoms is fully explained by perceived stress. So probably students, when they are close to defense, they suffer more symptoms because they are more stressed on a daily basis. But the direct effect for gender still remains significant. Here it is. It's still significant, which means that probably there are also some reasons why females report more somatic symptoms other than perceived stress. And of course, these additional possible mediators, we don't know what they are. We don't have them maybe even in our data set. So this mediation is only partial, and it's okay. But the fact that it's full for the year of thesis is already interesting, suggesting that doctoral students suffer because they are stressed. So I hope that you've got a general idea of how you can conduct and interpret mediation model. Doing it is very simple. It's a very simple approach. That's why people in social sciences quickly became very enthusiastic about mediation. There were many papers testing mediation models, and unfortunately, many of them made conclusions that were not really warranted by the data. As a result, now mediation is considered like a mauvais ton, not a very good idea. It's not as bad as stepwise or statistical regression, but it's probably just as bad as exploratory factor analysis. So it's not the best practice. Why? It's not because mediation is bad in itself, but because so many people have misapplied it. Rex Klein, in his nice paper published not so long ago, summarizes the wrong assumptions that people have about mediation. First of all, mediation is based on assumptions about the direction of effect, but it does not test these assumptions. So in our case with doctoral students, of course, year of thesis is more likely to be the cause, and perceived stress is more likely to be the outcome and somatic symptoms. You cannot say that because of suffering, students study longer. However, in some cases, the direction can go in both directions. For example, self-esteem and grades. Better grades because of higher self-esteem because of better grades. So these models going in both directions, they are equivalent statistically. And based on your statistical results, you cannot argue in favor of the direction of causality. You can only argue based on your research design. Another problem with mediation is that if your mediator is unreliable, your results will be biased. If your mediator is unreliable, instead of full mediation, you might get partial mediation. But it does not mean that there are other mediators. It's just because your mediator is measured with a low Cronbach's alpha, or just with a single item. And also, unmeasured third variables can contribute. If you have a third variable that is a common cause of all three variables, you can get a nice mediation. But if you controlled for this common cause, maybe there would be no mediation. So your mediation can be an artifact of an unmeasured third variable. And sometimes this unmeasured third variable can be a common method effect or something along these lines. Unfortunately, maybe many of our results are artifacts. And also, when people technically test for mediation, sometimes they start by testing full mediation. They don't include direct effect paths. They only include X, M, Y paths. And this approach is completely wrong, because if you fail to include direct effect, you will get wrong estimates of paths and a wrong estimate of indirect effect. So your results will be biased. That's why everyone says always test for partial mediation. And even if your direct effect is not significant, you say tada, you report it, but you still retain it in your model because you want unbiased estimates of indirect effects. And also sometimes an interaction between predictor and mediator can also bias these effects, but this is a little bit more complicated. So always test for partial mediation. And of course, in order to really make a claim about causality, you need a stronger research design. Of course, if you manipulate your predictor in an experiment, and then maybe you manipulation check your mediator, and then you have an outcome, it's very strong. Or if you have a longitudinal design, ideally you need 3 waves of measurement, and you measure your predictor, your mediator, and your outcome at each of those waves. But of course, maybe you don't use the measurement of predictor at time 2 and time 3. But here, for example, in this paper by Paul Jose, at time 1 he measured life satisfaction, happiness, and hope. At time 2 he measured happiness and hope. And at time 3 he measured hope. So this way the predictor, the mediator, and the outcome are measured at 3 different points in time. And you can also control for common method effects. You can control for pre-existing variance of this mediator and outcome. So this way your effects become much more trustworthy and your claim of mediation is much more well-founded. Of course, in a master's thesis, it's not possible to conduct such a longitudinal study sometimes, but maybe if it's a very short-term time frame, maybe you're still able to conduct it. Or if you're using an experimental design, of course, you can apply mediation easily. So this was a little bit about mediation. Of course, mediation is not the only possible model. There are some more tricky models because in principle you can combine mediation with moderation. You can have several mediators or several moderators. The moderator can mediate a path from X to M or from M to Y. So there is a whole family of models. They are all called conditional indirect effect models because this indirect effect from X to Y, it is conditional on some moderators. Moderators like here W. If you're interested in those models, check out a paper by Preacher, Rucker, and Hayes from 2007 where they explain how you test those models, and also you can see all the parameters that you need to include if you set this up. If you set up this model manually in Amos or in M+ or in some other path analysis software. What's important is that you need to have strong theory which predicts those interactions. If you don't have this strong theory, it will be a whole pain to test these models. There will be so many of them. How do you test these kind of models? Basically, this type of analysis is called path analysis. Already what we did with mediation just now, it was a variety of path analysis. Path analysis, it's a situation when you have several variables. They are all observed variables and they predict one another. But unlike regression, where you only have a bunch of predictors and a single outcome, in path analysis you can have several outcome variables at once, and also you can have mediators, also several of them. So a model can become fairly complicated. And this whole approach was proposed fairly long ago, in the 1920s, when people just would get a correlation matrix, and this guy Sewell Wright, he proposed a bunch of rules that you can apply to calculate those path coefficients by hand. But nowadays, of course, we have much better statistical tools, so we apply this path analysis in structural equation modeling packages such as Amos or M+ or EQS or R. There is a package called Lavan. And basically you start with a theoretical model which you invent in your brain, you draw it on paper, all the lines between your variables, all the arrows, which is the cause, which is the effect, and why. And then you set up this model in some structural equation modeling package. Some use equations when you have to actually write out that variable y equals x plus m, etc. Some of them use graphic interface. Amos, EQS, they use graphic interface, which makes it a bit more user-friendly. And then you basically feed your data to this package, your raw data, or just a correlation matrix, and you test if your model can fit with this data, if your model can reproduce the associations found in those data. And you use a chi-square test to see if there is a significant difference between the matrix reproduced by your model and the original data matrix. So if chi-square is significant, it means that your model fails to explain this data properly. But then if you see misfit, you also can explore modification indices to see, for example, which additional arrows, which paths are missing in this model. Of course, the software package does not know if these paths make sense or not. So it's up to you to reflect theoretically and think, does it make sense to include this path, or it's theoretically implausible? So this way you can improve your model to make it fit the data. But if you modify your model based on your data, of course you need to replicate it in a new sample. Otherwise, it is a bit of cheating. So let's explore a very simple example. I just tested a path model in M+. I could have done it in Amos. Unfortunately, SPSS does not allow to do it, and Jamovi does not have a module for path analysis right now when I'm recording this lecture, early 2021. But maybe in a few months, Jamovi will have a module, and that's going to be quite cool. So here I set up a path model where I included gender, year of thesis, satisfaction with supervisor, perceived stress, sleep quality, and symptom checklist. This causal hypothesis seems to fit the data fairly well. The chi-square is not significant, saying that we cannot reject this model. It fits the data fairly good enough. And there are the indirect effects on somatic symptoms mediated. So somatic symptoms is here. For somatic symptoms, we have this 0.70. It's unexplained residual variance. So 30% of individual differences in somatic symptoms we have explained with perceived stress and sleep quality, and with gender. And the indirect effects for all three predictors are statistically significant, suggesting that the effect of year of thesis is mediated by perceived stress, and the effect of satisfaction with supervisor is also mediated by perceived stress and sleep quality. This path, I think, is not significant. I just forgot to exclude it from the picture. And also, if we explore correlation matrix, we see that with each year of thesis, the dissatisfaction with supervision increases. So the closer the graduate students are to defending their PhD thesis, the less they are satisfied with their supervisors. And originally, when we were writing this paper, we thought of calling it, "Do you need to hate your supervisor in order to defend your PhD?" Then we called it in a some more boring way. Yeah, but this is the association that we see, and we can conclude that dissatisfaction with supervisor increases with each year in graduate school, and it's associated with perceived stress, with poor sleep quality, and with somatic symptoms. But of course, this formulation, this conclusion is formulated in terms of associations rather than causal effects, because we don't know, is it problems with supervisors that predict that cause stress, or is it perceived stress that causes problems with supervisor in the relationship? And yeah, so explanations can be different. Okay, so path analysis seems like such a nice statistical tool. Basically, you propose a very complex causal hypothesis, and then you can see if it fits the data. One important caveat is that if your model fits the data, it does not mean that this model is theoretically correct. Basically, statistical results only tell us that this model cannot be rejected based on statistical grounds. But is it true model? Is it a true model? Is it in line with substantive theory or not? We don't know. maybe another model could be equally good in terms of explaining the data. And as we have seen just before, the number of possible models already for 3 variables is almost 20 or almost infinity if you count nonlinear ones. So the number of possible models here is very, very huge. It's immense. So if you see that your model fits the data, it does not mean it's a good model. It's a good model if it's well based on theory and fits the data. Then it's a good model. So path analysis seems like such an exciting, perfect tool. Unfortunately, it has some problems. First of all, it works poorly in small samples. All these variables are observed variables. We don't really have much information from the data. As a result, we don't have much power to detect paths if they are not very strong, like 0.20. And sometimes we don't even have much power to reject a bad model if our sample is very small, less than 100 individuals. And another problem is that it assumes perfect measurement. Basically, the assumption is that every variable is measured with a Cronbach's alpha of 1. If your Cronbach's alpha approaches 1, it's not a problem. Or if your variable is objective, like a grade at school or gender, it's not a problem again. But if your measurement reliability is low, or you measure something with just a single item like sleep quality, you might get biased results. You might get partial mediation when in fact it's full, or you might not see an interaction when in fact it's there. So in general, if you are using psychometric measurements, it's generally better to use multiple indicators and to model your variables not as observed variables just by using some scores, but by modeling them as latent factors. And we'll explore this next time. As a result, you get unbiased estimates for associations between your constructs. But the disadvantage is that this approach is more complicated. So this is the reason why in psychology we usually tend to prefer structural equation modeling with latent factors instead of path analysis with observed variables. However, sometimes structural equation models become very complicated, they are hard to estimate, and we still use good old path models. And also in some natural sciences or in economics, where variables have more objective nature, like income or blood cell count, you can ignore measurement error and you can assume that reliability is perfect, and then path coefficients reflect reality really well. That's why people love path analysis in those sciences. In psychology, we still use it, but we are aware of its limitations. Okay, so this was a little bit of introduction into path analysis. I hope that you've gotten the general idea, and I hope that you are aware of the main limitation. We cannot be confident that perceived stress causes bad sleep, and that bad sleep causes somatic symptoms, and it's not vice versa. That's why we never published this path model, because based on this data you can create an infinity of such models. But of course, if we are doctoral students, we like this interpretation that it's troubles with supervisor that cause our problems and not vice versa. Okay, so thank you so much for your attention to this part, and right now we'll explore a different part of another type of linear models, general linear model.